Hello everyone. In this lesson, we'll learn about a feedback, or specifically it is about a negative feedback. So basically, first we look into what is a feedback and then move on to types of feedback, the advantages, characteristic and effect of a negative feedback, and we'll look into the real circuit of amplifier that employs a negative feedback, and lastly we'll conclude with a positive feedback and the relationship between it and an oscillator. Okay, so first for this particular topic, the topic learning outcome is first you should be able to distinguish between a positive and negative feedback. Okay, because we have two types of feedback. Okay, how to distinguish between these two, and then describe the advantages and the disadvantages of having a negative feedback, and then analyze any given circuit, whether it is a voltage amplifier, what are the feedback connection that is used with that particular amplifier, and then lastly it is about the positive feedback and Barkhausen criteria. Okay, so first we look what is a negative feedback in everyday life. This is an example of a shower. When you are in a bathroom, when the water is too hot, or you will turn it down, but if the water is cold, you turn it up. Okay, so this is how we control the temperature of the water. Okay, then another example is when you drive a car, when it is too slow, you push the accelerator. Okay, if you want to go faster, but if you are too fast, you will ease your foot off and you push your brake. Okay, and another example is when there is a person standing, when you are about to falling to the left or to the right, you will shift your weight so that you will be standing upright again, right? So this is an example of a feedback in everyday life. So this is another example in figure 1. When the water near the specified level, the valve is closed. So if you look over here, the valve is closed because it is at a high level. Okay, but if the water level is low, the valve is open and the water is flowing. So there is a one system which is, we call it as a closed loop. How do we tell the valve over here whether it should be closed or it should be open? Okay, so in this example, the floating ball over here is giving the right signal whether to open or to close the valve depending on the water level. Okay, so it is an example of a feedback also. Okay, so you want to control a system. Okay, so that is in everyday life. Now we look into in the electronic part, electronic circuit. What does it mean by a negative feedback? So in this block diagram, I have an amplifier over here. Some of the output is taken into a feedback network over here, and then it is summed up again at the input. This is the original source, so you sum the input over here with the feedback signal. So this is the summing node, and we want to minimize error, and you feed it back to the amplifier. So what will happen in this term? Okay, so you will get that the signal is being amplified because you have an amplifier over here, but once you put the output signal back to the feedback network, it will be attenuated. Okay, and you look over here, there is a plus sign and negative sign, meaning that the phase shift between the original inputs signal with the feedback signal over here is out of phase. This is for a negative feedback. Okay, so we want to minimize error. Okay, and okay, there are two types of feedback. One is a positive feedback, which is called the regenerative, because the output of the amplifier will be getting bigger and bigger. So that's why it is called regenerative. And the second one is negative feedback, which is the degenerative, whereby the output signal will be lower than the input signal. Okay, the basic idea of negative feedback is to trade off gain for other desirable properties. So that's why we call it degenerative, because the gain will be lowered. So this is a block diagram of a negative feedback. We have amplifier, feedback network. So this is the summing node. It is where or how we want to mix the input signal with the feedback signal. Okay, so the system, if you look over here, it say that the feedback tends to reduce the input to the forward path, meaning that you have an output signal, you go to the feedback network, the signal will be attenuated, but then it will be amplified again. So in the feedback forward, the input will be reduced because of the feedback signal over here. Okay, and the product of beta, which is the feedback network, multiply with A, the value will be positive. Okay, and the gain of the amplifier sometimes is called the open loop gain, and beta is the feedback network just now. Okay, so what about a positive feedback? For positive feedback, the block diagram is a little bit different. So if you see over here, there is no input signal. We look into details about the positive feedback later. Okay, so again, there is a plus sign over here. So you see over here, the feedback signal with the input signal is in the same phase. Okay, so for the positive feedback, the feedback tends to increase the input to the forward path. So looping around the loop over here, the signal will be amplified again and again. But if you look over here, it is different from the negative feedback. Okay, and the multiplication of the gain of the amplifier with the feedback network beta, the value is negative. Okay, and usually it is less than 1. Okay, so now we move on to another block diagram. Okay, in this block diagram, we have an amplifier without feedback, meaning that you have a signal over here, XS. It could be voltage. If it is a voltage, this will be Vs. If it is a current, it will be Is. Okay, so this is the general form, XS. This is input to the an amplifier over here, and at the output over here, XO, it could be also voltage or current. So we call it is an open system or amplifier without feedback. Okay, so from this figure, your output XO will be simply the input signal, which is XS multiplied with A, because the amplifier over here with a gain of A will amplify this signal. So your XO will equals to A multiplied with XS. So the gain, which is defined as the output signal over the source signal, XO over XS, is the overall gain of the system without feedback. Okay, so it could be voltage over voltage, voltage over current, current over voltage, or current over current. So we'll have 4 types of amplifier later on. Okay, so the A is open loop gain. Okay, now instead of connecting XS directly to the amplifier, we have taken the output, okay, which is the output of the amplifier. We take the output, goes back to the feedback network beta. We have the feedback signal over here, and we mix this feedback signal with the source signal over here. So there is an out of phase between the source signal and the feedback signal. We sum it, and this will be the input to the amplifier. So this is a closed loop system, or we call it amplifier with a feedback. Okay, so what will happen? We define first a feedback network over here, beta, as the feedback signal over the X out, because XF will be the output of this block diagram. The input is the output signal, so it will be XF over XO, which is a beta. And the gain without feedback just now, meaning that you just look over here, this part only. Okay, so your XO will be the output of the amplifier and the input is Xi. So A multiply with Xi will give you your XO. So the gain will be A equals to XO over Xi. This is without feedback. And with feedback, you have to find the XO with respect to the source signal over here. So it must count the effect of the feedback network over here. What will happen? So we call it as AF, and it is defined as X out over XS. So this is a closed loop gain. Remember just now A is open loop gain. Okay. So if you look over here, XF is equals to beta XO, because this is the output of this block diagram. The input coming over here is XO. So XO multiply with beta, you get XF. And then Xi over here, you're summing up the source signal over here with the feedback over here. Okay, so there is a plus and minus, it is opposite phase. Okay, so your Xi will equals to XS minus XF. Okay, and we define XF just now, which is beta XO. So now it is XS minus beta XO. And XO is the output of the amplifier. The input coming is Xi. So Xi multiply A is XO. Okay, XO equals to AXI. Substitute this into this equation. Okay, so you get XO equals to A multiply with XS minus beta XO. You just put in over here in place of Xi. And then you have to term XO over here. There is XO over here. So I bring this to this side. So factor it out. XO in bracket is 1 plus beta XO. Bring it over here. It will be plus beta A. You have A multiply with beta over here. And A equals to A multiply with XS. What we want to find is the XO over XS, which is the overall gain with feedback. So you have XS over here, XO over here. Simplify it. So your AF is equal to XO over XS equals to A divided by 1 plus A. What you see in this equation is your amplifier over here, the gain is A. And with a negative feedback over here, you have a beta. The gain will be divided by a factor which is 1 plus beta A. A divided by 1 plus beta A. So if you look over here, the denominator is greater than the numerator. So meaning that the overall gain, which is gain with feedback, will be less. So that's why we call the negative feedback is degenerative. So this is the equation. And so you have to remember this. AF will be A divided by 1 plus beta A. Okay, the gain will be less for a negative feedback. Okay, it is reduced by a factor of 1 plus beta A. And sometimes this 1 plus beta A is called deselectivity or simply D. Okay, this is a factor that will be used again and again in negative feedback. So I stop here first and we'll continue with the advantages of negative feedback. Thank you.